this light ray that's parallel to the principal axis, but it's not coming in at 90 degrees? Well, you draw the normal to the surface at this point, and because this is part of a sphere, right? So you go like this. So that's the normal, right? So the angle of incidence is this. So what must happen to the reflected ray? It needs to make an angle of reflection equal to the angle of incidence, so it's going to be like this. So that this angle of incidence here is equal to this angle of reflection. And if you consider the other light ray that's parallel to the two parallel rays that are parallel to the principal axis, right? If you consider the normal at this point, right? This light ray is coming in at an angle of incidence not equal to 0. So if you draw the normal, right? The normal is going to be like this. I mean, that's what I had over here too. This was the normal, right? So in this case, the angle of incidence is this. So the light ray reflects such that the angle of incidence is equal to the angle of reflection. Now, do the three reflected rays actually meet at some point? No, they don't. So how do we define a focal point and therefore a focal length? So we say the three rays, after interacting with the mirror, in this case reflecting from the mirror, right? They don't ever cross. So the focal point is not going to be over on the left-hand side of it here. But they seem to come from, like this one seems to come from here, this one seems to come from there, and this one seems to come from there. Notice that they seem to come from that point, but they don't. So that point is defined as the focal point, and the distance from that focal point to the vertex, that distance is defined as the focal length. So this distance over here. And just like in the case of the concave lens, where the light rays in that case, for the case of the concave lens, let me remind you, you had something like this. And you had three incident parallel rays of light coming in, and in the end they ended up going like this. Right? They don't ever cross. So if you trace them back, they seem to come from here, but they don't. And because they seem to come from there and they don't, we said that that was negative for the focal length. So in this case, we have the same situation, right? The light rays coming in parallel to the principal axis, they reflect from the mirror, they never cross again. Well, they never cross. And so, but they seem to come from that point, but they don't. So that's a focal point, this distance is a focal length, but we think of that as a negative focal length. So F is negative for a convex lens and concave mirror. I'm sorry, it's positive for a convex lens and concave mirror, but F, the focal length, is negative for a concave lens and a convex mirror. So you have to be careful here, because notice that the word convex doesn't tell you right away if F, the focal length, is going to be positive or negative. You have to read the next word. If it's a convex lens, the focal length is positive. But if it's a convex mirror, the focal length is negative. If it's a concave lens, the focal length is negative. But if it's a concave mirror, the focal length is positive. So what I do is I remember it for the lenses and then I switch it for the mirrors. Because a convex lens is a converging lens, which is a positive lens. So F is positive for a convex lens. So therefore, F is going to be negative for a and therefore it's going to be positive for a concave mirror. It switches. Yes? But do you see why it's positive and why it's negative? When there's a focal point, if the light rays actually make it to that focal point, then the focal length is said to be positive. If the light rays seem to come from that focal point, or they seem to cross at that focal point, but they don't, then the focal length is said to be negative. It's just that for the different geometries, you know, F is going to be positive for convex lenses and concave mirrors. So that takes care of this, of F. So sometimes you're solving a problem and they tell you something about the object, they tell you something about the image, but they don't tell you if the lens or the mirror was convex or concave. If you plug the value for the object distance and the image distance into that formula at the far end over there, and F comes out negative, and it's a lens, it's a concave lens. But if it comes out negative and it's a mirror, it's a convex mirror. Sometimes the question is, so what was it? Was it a concave or convex mirror or lens? So plug it into this formula, and if F comes out positive, if it was a lens, it's a convex lens. But if it was a mirror, it's a concave mirror. Can I erase this?
Can you leave the X one up for one more second?
So, number 2, the object distance S. So this is actually quite simple. It's simple because it's the same rule for whether it's a lens or a mirror, and I don't care if it's a convex or concave lens or mirror. It's the same. This is very simple. So S is positive, okay, if the object is to the left. This means in front of the lens, and it doesn't matter if it's concave or convex, or mirror, and it doesn't matter if it's concave or convex. If it's to the left, it's positive. And when is it negative? If the object, talking about an object, is to the right, which means behind, of the lens or mirror. So that's pretty straightforward. Can I erase this now?
Yes, sorry.
Okay, the next one, so we have 2 down. We got F and S. Now let me do M, the magnification. All right, so number 3, magnification. By the way, it's also called the lateral magnification. This is also simple. The magnification is positive. So this has to do with, comparing the image to the object. When the image is upright, what does that mean? If the image is upright. So, if I tell you that this is the image, is it upright or inverted?
It's upright.
Is what? Upright or inverted?
Upright.
Anyone else? I heard upright. Is it upright or inverted? How many of you agree it's upright? It's a lot of people. What about those who didn't raise your hand? Is it upright or is it inverted?
What is your definition of upright?
What does upright mean?
In this case, if the cap is at the top, then it's upright, from our point of view, right? It's a definition.
So, but that's not good enough. So, this is upright. This image is upright if the object is like this. What happens if the object is like this? Then this image is not upright. So it's gotta be relative to the object. If I position the object like this is inverted, relative to the object. If I put it like this, to you that looks inverted, but it is upright relative to the object if the object is like this. It's just that I didn't finish writing. So I meant to say when the image is upright, relative to the object. Right? So if the magnification is positive, the image is upright relative to the object. And the magnification will be negative when the image, and we're talking about an image, right, is inverted. But gee, what is inverted? Relative to the object. That is what sets a definition, relative to the object. So it has to do with how an image is oriented relative to the object. And the magnification is also defined as the height of the image divided by the height of the object. Yes? So, if I tell you that this marker is the object, suppose I tell you this marker is the object, and I tell you that the image is this red marker, what's the magnification? Negative? It's negative because it's inverted relative to the object. But what is the size of this image relative to this object?
2 times the size.
2 times the size. So therefore the magnification is
-2.
-2. Correct. What if the object is this red marker and the image is this? What's the magnification?
1/2.
1/2, 0.5 plus, right? Because it's upright relative, the image is upright relative to the object. So the magnification would be 1/2, 0.5, plus 0.5. What if the object is this and the image is this?
3 times?
3 times.
Why negative?
Oh, I'm sorry. I thought that was the other way around. I wasn't paying attention.
So you gotta look at both of them, because it's gotta be relative to this one.
Positive.
So it's plus, if this is the object, and this is the image, it's 3 times as big as the object, so the magnification is 3. The question is it plus 3 or minus 3? But it's upright relative to the object, so it's plus 3. The magnification is plus 3. Yes? So, is this image, let's say this is the object and this is the image. So, what's the magnification?
1.
Plus 1. What about now?
Minus 1.
Plus
1.
Plus
1.
Plus 1. Negative 1.
Okay? So go through that so you understand, right? So that's all there is to the magnification, right? So once you look at the value of the magnification, if you see a negative sign, it means that the image is inverted relative to the object, whatever the orientation of the object was, whatever that was. The image is oriented, if the magnification is negative, it is inverted relative to the object. The magnification is positive, then the image is upright relative to the object. And then given the size of the, if I get that the magnification is plus 10, that tells me that the image is 10 times as large as the object, and it is upright relative to the object. The algebraic sign tells me if it's upright or inverted, and the number tells me if it's larger or smaller, that if the image is larger or smaller than the object. Right? That's what that means. Right? So I want you to have an understanding of what that means. So I guess we have taken care of this. So the last one is the image distance S prime. When is the image distance S prime positive and when is it negative? So this is the image distance S prime, right? So when is the image distance positive? If it comes out positive, what does it mean? That's when the image has to do with the image is real. And the image distance is negative, that means that the image is virtual. That's it. The question is, what does real mean and what does virtual mean? So if the image is real, it means that wherever that image is formed, light rays actually went there to create that image. If the image is virtual, that means that wherever the virtual image is produced, light rays seem to go there to produce the image, but they don't. So either the light rays make it there or they don't make it there. If they make it there, it's real. If they don't make it there, it's virtual. Now, that means that we can have the following. So let's, and by the way, I'm not done. I'm gonna have to add something over here. Because this is enough, but I wanna show you how tricky it can be. So let's consider a convex lens that's thick in the middle, thin in the edge, right? So this is the convex lens, right? And I'm gonna draw the principal axis. Let's say the focal point is here. Focal point is here, like on the other side, right? So this is focal point F, focal point, and the distance is F, right? But I just want to label that as a focal point. What if I put an object? Over here? Object. So some distance away from the lens. In this case, I'm considering a convex lens. The question is, where roughly will this convex lens produce an image of this object? Roughly, where would it be? If you want to know exactly where it's going to be, you can just put it in, plug the appropriate numbers over here with the appropriate signs and solve for S prime, and then you'll figure it out. Now, where is this lens going to form an image of this object? So what I'm going to do is this. I'm going to figure out where the top of this object is going to be imaged. And then the rest of the body of that object is going to be imaged from there to the principal axis. And all I need are 2 rays. At the textbook, the authors, they use 3 light rays. But if 2 light rays meet somewhere, the 3rd, the 4th, the 5th, the 6th, the 17th, the 19th are going to meet there as well. So 2 is enough for me. And I draw one of them parallel to the principal axis. And we know what that's going to do. Remember what happens when we consider a light ray parallel to the principal axis hitting a convex lens? Where is it going to go after that? And through the focal point, right? And then I'm going to consider another light ray going through the middle of the lens. And I'm going to say that the lens is not very thick. It looks very thick over here, but it just, right? And so what happens is that, what I draw is going to be something like this. It's going to go right through it. There's going to be a little refraction here. It's going to go in, refract again. It'll just be laterally displaced. But, you know, for purposes of knowing where roughly the image is going to be, just go straight. Ooh, they seem too close over here. So therefore, the top of this object is going to be imaged at that point where those 2 light rays cross, and then if I consider other points, the rest of the object is going to be imaged over here like this. Now, this image, is this image, is it real or is it virtual? Real, because light rays actually went there to create the image. So first of all, it's real. Is it inverted or upright? So I expect the magnification to come out negative. If I were to calculate right. And it looks from my diagram, it looks bigger than the object, right? But that'll depend. It could be the same height, but you know, it could be enlarged. But if I want to be certain, I'll calculate the magnification. If it's a number greater than 1, it's enlarged. Right? But then just leave it there like that. So let me solve the same sort of problem, or consider the same sort of problem, the same lens, I mean by the same sort of problem. It's going to be the same lens. Here is the principal axis, and here's the focal point, and here's the focal point. Now, instead of placing the object over here, which is farther away than the focal point from the lens, I'm going to put it between the focal point and the lens. I'm going to put it somewhere in here. Same lens, same object, just positioned in a different location. So here's the object now. Where is this object going to be imaged by this convex lens? Well, 2 light rays. I go like this. From the top, I go straight to the lens, parallel to the principal axis, and then that light ray is going to go through the focal point, right? And then the other one, I'll just make it go through the middle of the lens. Now, do those 2 light rays actually meet on the right-hand side of this lens to form an image? No. So where is the image formed? So the light rays went through this lens, but they never crossed. So whatever image this lens produces is not going to be a real image. You say the following. You say, those light rays seem like this one, right? Seems to come straight from here. You think that the light is coming in straight. And this one seems to be coming from here. And at some point over here, they seem to come from there. So that's where the top of this object is going to be imaged. So now this is the image. And this image is it real or is it virtual? It is virtual. And by the prime, that means that S prime is going to be negative, right? Over here, it was real. So that meant that S prime is going to be positive. And the fact that it is inverted, the magnification is going to be negative, right? Is it inverted or upright relative to the object?
Okay.
Upright. So that means that the magnification is positive. Is it enlarged or the same size or smaller, reduced in size compared to the object? This one we can say is enlarged, right? So it is enlarged. So we can combine 2 and 3 over here and say that the magnification is more than 1. Right? Because if it's enlarged, the height of the image is greater than the height of the object. And it's upright, so it's going to be positive. So it's going to be some number greater than 1. When you use a convex lens like this, where you want to see an object, and maybe the object is small, and you want to see it enlarged, and not upside down, you want to see it, upright, then when the lens acts like this, when you place the object between the focal point and the lens, this lens acts as a magnifying lens. This is all a magnifying lens does. All you need is a lens, thick in the middle, fill in the edges, but you need to ensure that whatever you're looking at is placed between the focal point of the lens and the lens. This is why, for magnifying glasses, right, you can go just, you gotta put, if you wanna read or something, or wanna watch an ant walking around or whatever, right? Right? You have to bring it close to the object so that it meets this condition. Otherwise, you're gonna have an inverted image, and usually you put the object to be here, here's the lens, and you look this way. So essentially when you look this way, you don't see this, what you see is that. In fact, if you ever are relatively close to someone, close as in distance, not like, we're good friends or whatever. If you're relatively close to someone and you wonder, does that person have myopia or hyperopia, given that the person is wearing glasses? So if you look at them, carefully, straight in the eye while they're wearing the glasses, right? So these glasses have a focal point somewhere. If my eyes look larger than without the lenses, then these are acting as a magnifying glass. Therefore, it's a positive lens, and therefore I have hyperopia. I'm farsighted, not nearsighted. So just look at them and say, oh wow, she looks or he looks like, he's got big eyes. Just, or they seem to get bigger when he wears the glasses. Oh, definitely that person is farsighted. I mean, you can come close to me if you like and look at my eyes, and then they kind of look enlarged. Because the eyeball, right, it's the focal length of this lens is going to be like over here, and my eyeball is between the focal point and the lens. So the lens is acting like a magnifying glass. If you see someone's, yes, is this making sense? Right. So just if they look, the eyes look big, so that person is farsighted. I will talk about that. I think we said something about farsighted and nearsighted the other day, but then make the connection. So just because a lens is convex, it doesn't mean that it is going to produce a real image or a virtual image. It depends on where the object is placed. In this case, if the object is placed beyond the focal point, right, then the light rays, remember, this is a lens. This is a lens, right? So the light rays, it's a glass, right? So the light rays come in and they refract. They go to the other side. You're interested in what happens on the other side of a lens. For a mirror, the light hits the mirror and bounces back. So you're interested in what happens on the same side where the light came in for a mirror, right? So for a lens, the light comes in, it goes through the lens. Let's just say it interacts with the lens. But then what happens after interacting? They meet to form an image. And that image is real. But if for this lens, right, the light rays come in, they go through the lens, but they don't meet over here. So the image is not going to be real. But the image is from over here where the light rays seem to come from, but they don't. So this image is virtual. So for a lens, since the light rays go through the lens, if the light rays form an image to the right of the lens, it's going to be a real image. If the lens forms an image to the left of the lens, it's going to be a virtual image. So I can add over here. S is plus when the image is real, right? This means to the right of the lens. That's number one. Now I have to investigate what happens with the mirror. Now, S prime is negative when the image is virtual, which for a lens would have to be what? To the left of lens.
Of a mirror? Or wait, no. Oh, my, sorry.
To the left of the lens. Now, for a mirror, what happens? For a mirror, the light rays come in, they hit the mirror, and then they come back. So if they meet to form an image on this side, they actually went through to form that image and met at that point, so the image is going to be real. So for our mirror, it's going to have to be to the left of the mirror. But let me just go through that over here. Let's consider a concave mirror. So that's the one like this. Okay, the way that I figure this out, if it's bent like that or the other way, is I always think I'm coming in from this side, and that wall is flat. If I start carving on the wall, it's like I'm making a cave. So it's going to be curved like that. I don't know if that makes sense to you, but so you have the principal axis. Let's say the focal point is here, and I place the object over here. Object. So where would this mirror create an image of this object? So all I need are two light rays. I'm going to draw one like this, parallel to the principal axis. And what is it supposed to do after it hits the mirror? You can look at your notes. It goes to the focal point, right? I should have paid special attention to the reflection, because that's what we're interested in. So I'll use a different color for this reflection here. Now, the other light ray that I will consider is going to the vertex. So I'll go like this. And then that's the angle of incidence. And so it's just a reflection, right? It's going to have to reflect like this. So notice they meet right there. So that's where the top of this object is going to be imaged, and the rest of the object will be imaged like this. So did the light rays actually cross at that point to form that image? The light ray hit the mirror, came back, and crossed right there. So this image, this is real. Right? So S prime is positive. So it would have to be to the left of the mirror. Notice that in this case it is inverted relative to the object. So that means that the magnification is negative. Now, what if you consider the same mirror, but now, here's the focal point. Now you place the object between the focal point and the mirror. So where will this image be created? By this same mirror, concave mirror. Same object, same mirror. So then I go like this, parallel to the principal axis, and then after reflecting, it's going to go through the, oops, I meant to use the other color. It's going to go through the focal point. Like that. And then the other light ray that I consider is going to the vertex. So I go like this. That's the angle of incidence. So it'll reflect like this. So this is the angle of reflection. Now, do the reflected light rays ever cross? So you're not gonna have a real image on this side. So where do those light rays seem to come from? This one seems to come, just extend it back, extend this one back. They seem to come from here. So the head of that object image will be here. So this is the image. And is that image real or virtual?
Virtual.
Because the light rays never make it to that side of the mirror. Is it upright or inverted? So that means that the magnification is plus, right? Is it enlarged or reduced? So we can say that the magnification is gonna be plus and more than 1, so it's gonna be greater than 1.
At science night, is this why our
What's that?
at the science night? Remember the giant mirror? Is this why you looked enlarged in it?
Exactly. But let me go get it so that